We next need to move into actually making the confidence intervals for population variance and standard deviation. I don't know why I didn't capitalize that. All right, so here's the formula for variance. Now remember, variance is just the standard deviation squared. So for sigma squared, this is your confidence interval. You have a lower bound of this number and an upper bound of this number. Okay. Keep in mind that you still have to have a simple random sample from a normal population. The population still has to be normal, just like it was for both the confidence intervals for the mean and the confidence intervals for proportions, because remember, that's where the chi-square distribution was created from in the first place, was this data was normal when I had the computer calculate it. So we need it to still be normal. Even though we're not going to be working with the normal distribution, we're working with the chi-square distribution. But the chi-square distribution is developed from that normal distribution. So it's normal with a mean of mu, standard deviation sigma, and then the confidence interval is this. And the text doesn't write this down, but I just put it in there. If it's this way for sigma squared, i.e. the variance, then it's this way for the standard deviation. You take the square root of both of those values, because remember, that's how variance and standard deviation relate to each other. So if you know one, you should very easily be able to find the other. All right, so I have down here the GRE scores. It's the GRE scores. GRE is like the SATs, but for graduate students. And this is for the verbal reasoning portion. So it has several portions. This is the verbal portion. And these are a random sample of 10 students that took the test. So the first thing you need to know is you need to verify that this comes from a normal distribution, because we need that normal distribution, right? It has to come from a normal population in order to be able to do any interval. So we need to prove that it's normal, and we were not told or given that information ahead of time, and our sample size is less than 30. So remember, from 8.1, as long as the sample size is bigger than 30, then you can kind of fudge your way through it and say, yeah, it's normal enough. But we don't have a large sample size. We have a small sample size, and we aren't given enough info to know that it was normal to begin with. So we have to draw one of these graphs, right? We have one of these plots to prove that the data is normal, and then we can proceed with constructing the interval. And it is normal, right? Because the dots are all in between those two boundary lines. All right, so now we're going to actually do some of the work. So the first thing we want to know are, what are the point estimates for the population variance and the population standard deviation? Point estimates are kind of your best guess. So our best guess for each of these, hold on one sec. All right, our best guess for the population variance sigma squared is S squared, the sample variance. How do I put that? Sample variance. And our best guess for the population standard deviation, sigma, would be the sample standard deviation, S. Okay. Now, how are we going to get those? Well, we learned that way back in chapter 3. Right, we have some data, and I'm going to take these numbers, I'm going to go put them into Excel. I'm going to need a new example. So this is 9.3, example 3. And I'm going to have to go put these numbers in. Hold on one second, I'll type these up. All right, there they are in there. So I need the variance, so equals var. Now, in old school Excel, it's just var. In the new one, it's var.s, which I like better because it reminds me that it's the sample. But whichever one you've got, that's what you got to work with. So there's the variance. I better make a note. Sample variance. And so this is our best estimate for the population variance. And then for standard deviation, you can do it two ways. You could just type equals stdev.s or stdev. Or remember that it's equal to the square root of that variance that you found, right? So there's an intimate relationship between those two. So that's the sample standard deviation. Okay, there they are. Bolded and highlighted, and I'm going to put them back in my notes. There we are. Now we need to construct this interval. So the interval we're making one for the population variance. So there is a formula for it. Let me go grab it. And I've actually got it all done right here, but let's see the parts of it. So you take n minus 1, which in our case is 9, right? 10 minus 1, 9. And hold on one second. There we go. 9, and then we have the variance, sample variance that we came up with before, which was 1118.9, right? Now the real question is, where do I get the chi-square values from? So remember that our degrees of freedom was what I just said, degrees of freedom, df, equals n minus 1, which is 9. So I'm going to use that row in the chi-square table. And then your alpha. So alpha over 2 is equal to 0.025 again for this one. And again, know that it will not always be the case. It just was here, which is 0.975. Right? So those are the columns in the table. And then I can go right back here to the table. So you go 0.025, drop down to 9, right there, 19.023. And then over here, 0.975, drop down to 9, 2.7. So that's where the two numbers came from for the denominators, right there, 19.023, 2.7. So they come from the table. And then you just use your calculator to divide it, and you've got it. So that's how to do it by hand, basically with the table. So by hand with the table to help you. Let's also do it with StatCrunch. Or we could use Excel, honestly. It's kind of easy. But so if we want to do the lower limit, well, let's find the chi-square distribution values. So the chi critical values is what they're called, critical values. So you have the lower one, which is equal to chi dot inverse 0.025 comma 9. There we go. Oops. Whoops, I forgot. It's chi-square inverse, chi-sq. There we go. That's the new function. Chi-square dot inverse. There it is, 2.7, just like the table said. And then the upper one would be equal to chi-square dot inverse. You can either use chi-square inverse again and just do 975, or you can do chi-square inverse dot RT, whichever way you like. So I'll do chi-square inverse. So 0.975 comma 9. There we go. And then to find the lower value, so the lower limit, it's equal to 9 times that value, sample variance, divided by this value right here, 19.023. You flip them. So whichever one was the upper chi-square critical value, that's the one that you divide by first. And then the upper one is the same deal. It's 9 times 1118 divided by the 19. Oh, excuse me, the 2.7. There you go. There's both values with Excel. What about StatCrunch? StatCrunch should be easier because it usually is for most things. So let's go to StatCrunch. Go to Stat. Oh, before I go to Stat, hold on. I'm actually going to do this by copying and pasting this data in right here. Okay. Oh, hold on. Let me make that bigger so you can see it. There we go. That's a little bit better. Okay, so here are our numbers right here. So you go to Stat, you go to Variance. That's the one. One sample. Now you have a choice here. This particular one, we had the data, so you can choose with data. If you didn't have the data, and for example, I just told you that the variance was 1118 and change, but didn't give you the actual raw numbers, then you'd choose summary. So this one, we actually have the data sitting there. So I'll choose with data. There's the GRE verbal. Next. And we're going to choose confidence interval. So click down here. We wanted a 95% and just say calculate. And there it is. I can copy and take it back to Excel and paste. I mean, really, StatCrunch is so easy for this. It's even easier than by hand. StatCrunch is easier than doing it with Excel. StatCrunch is the best for this stuff. But for your assignments, of course, you want to know how to do all the ways. On the exam, of course, you won't have Excel and StatCrunch available to you, so you'll have to use the table. But the advantage of Excel and StatCrunch is, one, StatCrunch in particular is really fast and easy. But two, you're not limited to only the values that they have in the table. When you use by hand methods, you're struggling because you're always limited to whatever values for chi-square that they happen to have in the table here. But with Excel and StatCrunch, we're not limited like that. We could have huge data sets, big numbers, and it would all calculate super, super easily. Okay? So I'm going to, for the sake of it. And the other advantage, by the way, to StatCrunch is that when it did that calculation, it found the sample variance, the degrees of freedom, and all that stuff for you without you having to sit here and find the variance first and find the standard deviation. You didn't have to do any of that. StatCrunch does it all in one fell swoop. You just tell it what the numbers are, and it'll calculate everything for you. That's why StatCrunch is awesome. All right, now what about the standard deviation? Now that StatCrunch won't do for you. So you have to do it kind of on your own. If I give you this one for variance, or if you found it yourself, how does the one for standard deviation relate? And the answer is, well, it's the square root of these ones, right? So the confidence interval for the standard deviation is the square root of both of these. So all you have to do is take the square root of both of these numbers. Oops, square root of that one, square root of that one. So you make a calculator or computer or Excel find those values for you. Hold on one second. I'm going to go do it in Excel because Excel will be quick and easy. And you can do it with these numbers we already found, SQRT from Excel, right there. Or you can do it down here with the StatCrunch numbers, because if you found them with StatCrunch first, then you could do it that way. Or if you did it by hand, you could grab a calculator and do it that way. One way or another, you've got to get the correct numbers. And this is for standard deviation. The lower limit is the 72. The upper limit's 192. Okay. So I'm going to go copy and paste these in, I guess, just for my own benefits. That way I've got them in there. All right, so back to this. It's 192, oh, excuse me, 72, 72.5296, comma, 192.5036. Good enough. All right, now how do we interpret that interval? Well, we interpret it the same way we interpreted the ones before in chapter 9.1 and 9.2. Namely, we are 95% confident that the true standard deviation for GRE verbal scores or verbal GRE scores is between 72.53 and 192.5. We always started off with we are 95%, 99%, 190, whatever percent confident. And then you have to write in English what this was. This was the population standard deviation. So the true standard deviation for, I should say here, all verbal GRE scores. All right, note that the margin of error could not be simply found by subtracting the point estimate. So let me prove that to you. Hold on one sec. There we go. So recall our standard deviation was 105.446. So if this was going to work, it would be able to take that point estimate, that middle value, take away the lower bound. There it is. And then you take the upper bound minus that point estimate, and you get a bigger number. Right, because it's skewed left. The chi-square distribution. Or skewed right, excuse me. There we go. Because the chi-square distribution is skewed right, this number right here, between the upper and the middle, well, it's not really the middle, that's kind of the problem, but between the upper and the point estimate will always be larger than the point estimate. Here, let me put that down. Point estimate, which is the standard deviation minus the lower. They'll never be the same, and it has to do with the fact that it's skewed right, and that's causing it, this upper part, to be bigger than this lower part. Which is why we can't do what we did before with making a confidence interval. This isn't a plus or minus thing. Remember the other ones would say things like x bar plus or minus t. We don't have that here. It's not possible. And it's because we don't have that symmetry that we had in the other sections with the z and the t distributions. The chi-square distribution doesn't have that symmetry. So we're stuck doing it with this other formula. Well, we only have one page left, and that's reading computer output. I'll see you back here for that example.